This is the second part of module number 2, Hypothesis Testing and Analysis of Variance of STAT 560, Applied Business Research and Statistics. In the previous part, we have some examples of descriptive statistics. Now we're going to talk about inferential statistics. Let's look at this example. The standard deviation associated with the manufacturing process of 15-ounce jam jars is known to be 1.3 ounces. A random sample of 100 jars resulted in a mean of 14.8 ounces. The question we have is the machine that fills the jars properly calibrated? This is an illustration of a common situation in the statistics. We are trying to infer conclusions relative to the population, in this case all the jars filled by this machine, by analyzing a sample of 100 jars. We cannot say that the mean of the population is the exact mean of the sample, but we can calculate a confidence interval for it. Our objective is to determine with a certain level of confidence the interval for the mean of the population based on the mean of the sample. We also know what the standard deviation of the population is in this particular case. The lower limit of the confidence interval is given by deducting from the mean of the sample a certain number of standard deviations multiplied by the standard deviation of the population and dividing that number by the square root of the sample size. The upper limit of the confidence interval is given by the same mean, but just adding the same calculation that we had on the lower limit of the confidence interval. In our case, the mean of the sample is given by 14.8 ounces. Then we have the number of standard deviations associated with 90% confidence interval, and we will look into how that is obtained from the normal distribution table, times 1.3 ounces, which is the standard deviation of the population, divided by 100, which is the number of jars we decided to measure, and in reality is the square root of 100. The upper limit again is calculated using a similar formula. The only difference is that we change the negative to a positive sign. We can now state with 90% confidence that the mean of the population is between 14.586 and 15.014 ounces, which indicates that the jar filling equipment requires no calibration. The value of Z comes from the normal standard distribution table, which is included as an appendix to the notes of the course. Confidence intervals for populations are determined based on a sample size. The larger the sample, the narrower the confidence interval. However, large sample sizes are sometimes not feasible, but in most cases costly. It is therefore important to minimize the size of the sample and keep them as large as they need to be in order to give us the proper level of information. One of the drivers of the sample size is the margin of error, in this formula given by the letter H. That is the tolerance we're willing to accept. We also know that the larger the standard deviation, the larger the sample size needs to be. And that's why we see the standard deviation on the top side of the equation, and we see the tolerance level as a denominator. So the size of the sample is given by the number of standard deviations associated with the confidence interval, taken to the square, multiplied by the standard deviation of the population, also to the square, and divided by the tolerance level, also to the square. Let's take a look at a different problem. We have 3 container crane operators working in a terminal that appear to have different productivity levels. In order to test that, we conduct an experiment. The productivity for every crane driver is measured during 5 equivalent jobs. And the question we have to answer is the productivity for these operators comparable? So we have Carl, Paul, and Chris running the same crane, and we see that Carl has a mean of 24.9 moves per hour, while Paul completes his task at a rate of 22.6 moves per hour in average, and Chris 20.6 moves per hour in average. And we have the 5 samples here. It's not necessarily easy to conclude from the mean that Chris has lower productivity than Paul and Carl, and that Carl is the most efficient. These are results of a rather small sample. So we're going to use another technique, which is the analysis of variance. The population here is the productivity achieved by every one of the drivers. So the null hypothesis is that the 3 populations are the same. In other words, there is no difference between productivity, and the differences that we see on that sample are purely because we are looking at samples. The alternative hypothesis is that these 3 productivities are in fact different. So our objective by this hypothesis testing is to see if we are able to reject or not the null hypothesis. So we apply the F distribution test. We calculate F by using the analysis of variance and obtain the number of 25.602. When we look at the F distribution table, which is also part of the appendix of the notes, we see that the F for significance level of 5% is 3.89. The calculated F is greater than the significant F. Therefore, the null hypothesis is rejected, which is the hypothesis up here. The conclusion is that the productivity of the crane drivers at the level of significance of 5% appears to be different. The calculations associated with this example are presented as video tutorial 2 of this module. We took a look earlier at the data associated with consumer habits in different regions of the country. Let's try to answer this question. Are consumer habits different by region? This analysis is part of video tutorial number 3 for this module.